Well, welcome back to our course on computer organization and architecture. I'm going to go through chapter 3 at this point, and so this gets into our next major section. We went through a couple lectures talking about an introduction for computer architectures, and now we're going to get into specifically into the computer system. So this first chapter is going to be a top-level view of the computer function and interconnection. And then we're going to actually be spending some time going through a couple different concepts in terms of memory and input and output. So that's just something to keep in context as we move on for here. But this is going to be a nice overview of the computer capability operating as a system. And so this is going to be a top level view of that. And then we'll get a chance to get into some more detail as we get into the following chapters. So we'll come back to this chart at the end of the lecture, but this is just a reminder of the things that we're going to talk about. We'll be talking about computer components, talk about the von Neumann architecture in some more detail, talk about the computer functions that need to take place, the fetch execute cycle, the ability to have interrupts, to have more surgical operation, and thinking in more in depth in the input and output functions. We're thinking about interconnection structures, bus interconnections, and then we'll have a couple of things here, thinking of point-to-point interconnects, and also PCI Express, and have some details that get into some of the ways that is utilized in computing systems. So as discussed in chapter 1, virtually all contemporary computer designs are based on the concept developed by von Neumann at the Institute for Advanced Studies at Princeton's. Such a design is referred to as a von Neumann architecture and has 3 key concepts. First of all, the 3 components are the CPU, the memory, and input and output. But let's think about some concepts related to this. So the data and instructions are stored in a single read-write memory. Number 1, the content of the memory are addressable by location without regards to the type of data contained there. And 3, the execution occurs in a sequential fashion from one instruction to the next. So the reason behind these concepts was discussed in chapter 2, but perhaps getting a little bit of review is helpful. And so there is a small set of basic logic components that can be combined in various ways to store binary data and perform arithmetic and logical operations on that data. If there is a particular computation to be performed, a configuration of logic components designed specifically for that computation could be constructed. We can think of the process of connecting the various components in the desired configuration as a form of programming. The result of, quote, program, the program is the form of hardware and is termed a hardware program. So those are some things to be thinking about. So we talked about the von Neumann architecture again. We talked about hardwired programming. Let's continue on here. So here is an illustration of hardware and software approaches. Now consider this alternative. Suppose we construct a general purpose configuration of arithmetic and logic functions. A set of hardware will perform various functions on data depending on control signals applied to the hardware. In the original case of customized hardware, the system accepts data and produces results. So that's in figure 1A up at the top here. With general purpose hardware, the system accepts data and control signals and process results. Thus, instead of rewiring the hardware for each new program, the programmer merely needs to supply a new set of control signals. This is a powerful way of how you can have programmable activity within the processing environment. How should we control signals be supplied? The answer is simple but subtle. The entire program is actually a sequence of steps. At each step, some arithmetic or logic operation is performed on some data. For each step, a new set of control signals is needed. Let us provide a unique code for each possible set of control signals and let us add to the general purpose hardware a segment that can accept a code and generate a control signal. So that's what we're seeing below in this part B of this figure. Okay, let's talk about software and input-output components. First of all, programming is now much easier. Instead of rewiring the hardware for new programs, all we need to do is provide a new sequence of codes. Each code is in effect an instruction, and part of the hardware interprets each instruction and generates control signals to distinguish this new method of programming. A sequence of codes or instruction is called software. So that's what we're seeing up here in this top. So we're seeing this figure. It indicates two major components of the system: an instruction interpreter and a module of general purpose arithmetic and logic functions. These two constitute the CPU. Several other components are needed to yield a functioning computer. Data and instructions must be put into the system. For this, we need some sort of input modules. The module contains basic components for accepting data and instructions in some form and converting them into an internal form of signals usable by the system. A means of reporting results is needed, and this is in the form of an output module. Taken together, these are referred to the I/O components. So thus we've seen the software. We talked about that. We saw discussion a little bit at a high level here. For the CPU, we have the input and output modules. And another thing in the von Neumann architecture is the memory. So that's what we have here for a nice perspective of what that is. And so let's talk about a couple different concepts. This is where we're going to get into some more details about memory and I/O. So we have the memory addressable registers, the memory buffer registers, the I/O and address registers, I/O buffer registers. And so a couple different types of registers that are part of the process. So another important component is needed as we're talking about this. So input devices will bring instructions and data in sequentially, but a program is not invariably executed sequentially. It may jump around. So that is the IAS jump instruction. Similarly, operations on data may require access to more than one element at a time in a predetermined sequence. Thus, there must be a place to store temporary both instruction and data information. That module is called memory or main memory to distinguish it from external storage or peripheral devices. Von Neumann pointed out that the same memory could be used to store both instructions and data. The CPU exchanges data with memory. For this purpose, it typically makes use of two internal, that is to the CPU registers, a memory address register. So that's what we're seeing up here, which specifies the address in memory for the next read or write, and a memory buffer register, MBR, which contains the data to be written into the memory or receive the data read from memory. Similarly, an I/O address register specifies a particular I/O device. An I/O buffer register is used to exchange the data between an I/O module and the CPU. So we see that these registers are an important part of what we need. So in this figure, we see an illustration of the top level components and suggests the interactions among them. A memory module consists of a set of locations defined by sequentially numbered addresses. Each location contains a binary number that can be interpreted as either an instruction or data. An I/O module transfers data from external devices to CPU and memory and vice versa. It contains internal buffers for temporarily holding these data until they can be sent on. So in this figure, we see the basic instruction cycle. And so the fetch execute is something that you do as long as you're in the program. So this basic function is performed by a computer in the execution of a program, which consists of a set of instructions stored in memory. The processor does actual work by executing instructions specified in the program. This selection provides an overview of the key elements of program execution. In the simplest form, instruction processing consists of two steps. So the processor reads, fetches instructions from memory at one time and executes each program. Program execution consists of repeating the process of instruction fetch and instruction execute. The instruction execution may involve several operations and depend on the nature of the instructions. The processing required for a single instruction is called an instruction cycle. Using the simplified two-step description given previously, the instruction cycle is depicted in this figure. The two steps are referred to as the fetch cycle and the execute cycle. Program execution halts only if the machine is turned off, some sort of unrecoverable error occurs, or the program instruction that halts a computer is encountered. So you can have a halt instruction to end that cycle. So let's think a little bit more about the fetch cycle. So at the beginning of each instruction cycle, the processor fetches an instruction from memory. In a typical processor, a register calls the program counter, holds the address of the instruction to be fetched next. Unless told otherwise, the processor always increments the PC, that's the program counter, after each instruction fetched so that it will fetch the next instruction in sequence. That is the instruction located at the next higher memory address. So for example, consider a computer in which each instruction occupies one 16-bit word of memory. Assume that the program counter is set to memory location 300, where the location address refers to a 16-bit word. The processor will next fetch the instruction at location 300. On succeeding instruction cycles, it will fetch the instruction from location 301, 302, 303, and so on. This sequence may be altered as due to various things. For example, that the fetch instruction is located in a register in the processor known as the instruction register. The instruction contains bits that specify the action the processor will take. The processor interprets this instructions and performs the required action. Okay, so here we have the action categories. And so we have the processor memory. So the data may be transferred from processor to memory or from memory to processor. We have the processor and I/O. The data may be transferred to or from a peripheral device for transferring between the processor and an I/O module. The data processing of the processor may perform some arithmetic or logic operation on data. And finally, control and instruction may specify that the sequence of execution be altered. So those are things that we can be considering as we're working through that cycle. So here in this figure, let's consider a simple example using a hypothetical machine that includes the characteristics listed here. The processor contains a single data register called an accumulator. Both instructions and data are 16 bits long. Thus, it is convenient to organize memory using 16-bit words. The instruction forms 4 bits for the opcodes. That there can be as many as 2 to the 4th or 16 different opcodes, and up to 2 to the 12th, 496, that's 4 kilobytes worth of memory can be directly addressed. So now we're getting a chance to see what a 16-bit word is capable of doing. In this illustration, we're illustrating a partial program execution showing the relevant portions of memory and processor registers. So the program fragment shown as the contents of the memory word at address 940 to the contents of the memory word at address 941 and stores the result in the latter location. 3 instructions, which can be described as 3 fetch and 3 execute cycles, are required. The program counter contains 300, the address of the first instructions, thus the instruction, the value 940 in hexadecimal, is loaded into the instruction register IR, and the PC is incremented. Note that this process involves the use of a memory address register and a memory buffer register. For simplicity, these intermediate registers are ignored. The first 4 bytes, first hexadecimal digit in the IR indicates what the AC is to be loaded. The remaining 12 bits, 3 hexadecimal digits, specify the address, 940, from which the data are to be loaded. The next instruction, 5941, is fetched from location 301, and the PC is incremented. The old contents of the AC and the contents of the location 941 are added, and the result is stored in the AC. The next instruction, 2941, is fetched from location 302, and the PC is incremented. The contents of the AC are stored in location 941, and so thus we see that all coming together. And so in this example, 3 instruction cycles, each consisting of a fetch and an execute cycle, are needed to add the contents of location 940 and 941. With a more complex set of instructions, fewer cycles would be needed. Some other processors, for example, include an instruction that contained more than one memory address. Thus, the execution cycle for a particular instruction on such processors could involve more than one reference to memory. Also, instead of memory references, an instruction may specify an I/O operation. Okay, and in this figure, the execution cycle for the particular instruction may involve more than one reference to memory. Also, instead of memory references, an instruction may specify an I/O operation. With these additional considerations in mind, and this figure provides a more detailed look at the basic instruction cycle of figure 3.3. The figure is in the form of a state diagram. For any given instruction cycle, some states may be null and others may be visited more than once. The states can be described as follows. Instruction address calculations determine the address of the next instruction to be executed. Usually this involves adding a fixed number to the address of the previous instruction. For example, if each instruction is 16 bits long and memory is organized into 16-bit words, then add 1 to the previous address. If instead memory is organized as individually addressable 8-bit bytes, then add 2 to the previous address. There's the instruction fetch. We read instruction from the memory location into the processor. We have the instruction operating decoding. We analyze instruction to determine the type of operation to be performed and operands to be used. We have the operand address calculation. If the operation involves reference to an operand in memory or available via I/O, then we want to determine the address of the operand. We have the operand fetch the operand from the memory or read it in from I/O. We have the data operation, which is performs the operation indicated in the instruction. And then we have the operand store, write the results into memory or out to I/O. So there's a lot of things that are going on here, but hopefully that gives you a perspective, and we'll be coming back to this type of a way of looking at processing as we move forward in the course. So let's go ahead and move on to the next chart here. So here, let's talk about classes of interrupts. So we can have a program interrupt, timer interrupt, input and output, and failure, hardware failure interrupts. And so each one of these needs to be captured as we're thinking about how we're going to organize our computing environment. So in this figure, we're looking at the program flow of control with and without interrupts. And so we can see that without an interrupt, things are going to go in one way. When there is an interrupt, we're going to go do that, whatever it's asking us to do. And then we go back and finish what we were doing before, the baseline performance. So interrupts are provided primarily as a way to improve processing efficiency. For example, most external devices are much slower than the processor. Suppose that the processor is transferring data to the printer using the instruction cycle scheme of figure 3.3. After each write operation, the processor must pause and remain idle until the printer catches up. The length of this pause may be on the order of many hundreds or even thousands of instruction cycles that do not involve memory. Clearly, this is a very wasteful use of the processor. So in this figure, we have an illustration that shows that the state of affairs. The user program performs a series of write calls interleaved with processing. Code segments 1, 2, and 3 refer to segments of the instructions that do not involve I/O. The write calls are to an I/O program that is a system utility, and that will perform the actual I/O operation. The I/O program consists of 3 sections. There's a sequence of instruction labeled 4 in the figure to prepare for the actual I/O operation. This may include copying the data to the output into a special buffer and preparing the parameters for a device command. The actual I/O command without the use of interrupts. Once this command is issued, the program must wait for the I/O device to perform the requested function. The program might wait by simply performing a test operation to determine if the I/O operation is done. The sequence of instructions labeled 5 in the figure to complete the operation. This may include setting a flag indicating the success or failure of the operation. Because the I/O operation may take a relatively long time to complete, the I/O program is hung up until and waiting for the operation to complete. Hence, the user program is stopped at all points of the write call for some considerable period of time. With interrupts, the processor can be engaged in executing other instruction while an I/O operation is in progress. So that gives us an idea of how this would be working. We see a couple examples of what would happen when we have I/O here, and we have the 1, 2, 3, and then the 4 and 5 elements here for a couple cases. The no interrupt case, the interrupts with a short I/O wait, and an interrupt with a long I/O wait. So let's go ahead and move on here. From the point of view of the user program, an interrupt is just that, an interruption of the normal sequence of execution. When the interrupt processing is completed, execution resumes. Thus, the user program does not have to contain any special code to accommodate interrupts. The processor and the operating system are responsible for suspending the user program and then resuming it at the same point. So in this figure, to accommodate interrupts, an interrupt cycle is added to the instruction cycle, as we see in this figure. In the interrupt cycle, the processor checks to see if any interrupt has occurred, indicated by the presence of an interrupt signal. If no interrupts are pending, the processor proceeds to the fetch cycle and fetches the next instruction of the current program. If the interrupt is pending, the processor does the following. It suspends execution of the current program being executed and saves its context. This means saving the address of the next instruction to be executed and any other data relevant to the processor's current activity. It sets the program counter to the starting address of the interrupt handler routine. The processor now proceeds to the fetch cycle and fetches the first instruction in the interrupt handler program, which will service the interrupt. The interrupt handler program is generally part of the operating system. Typically, this program determines the nature of the interrupt and performs whatever actions are needed. In the example we have been using, the handler determines which I/O module generated the interrupt and may branch to a program that will write more data out to the I/O module. When the interrupt handler routine is completed, the processor can resume execution of the user program at the end of the interrupt. So there's a lot of going on here, but hopefully this gives you an idea of how this would be a modification of the fetch execute process by a way that we're handling interrupts. So to appreciate the gain in efficiency, consider figure 310, which we're showing here, which is a timing diagram based on the flow of control in figure 3.7a and 3.7b. In this figure, user program code segments are shaded green and IO program code segments are shaded gray. Figure 310A shows a case in which the interrupts are not used. The processor must wait until the IO operation is performed. Figure 3.7b and 3.10b assume that the timing required for an IO operation is relatively short, less than the time to complete the execution of the instruction between write operations in the user program. In this case, a segment of code labeled code segment 2 is interrupted. A portion of the code 2A executes while the IO operation is performed, and then interrupt occurs upon the completion of the IO operation. After the interrupt of service, execution resumes with the remainder of the code segment 2. Okay, so just to finish up here, we're looking at a program timing for a short IO wait. We walked through that. And then in this next chart, we have the program timing for a long IO wait. And so we have this same kind of process that we looked at before. And so this type of diagram is one of the ways we're trying to gain some insight in this. So for this case, the more typical case, especially for a slow device such as a printer, is that the IO operation will take much more time than executing a sequence of user instructions. So this figure is trying to give some type of a sense of what that is. And so referring back to 3.7c indicates the state of affairs. In that case, the user program reaches the second write call before the IO operation spawned by the first call is complete. The result is that the user program is hung up at that point. When the preceding IO operation is completed, this new write call may be processed and a new IO operation may be started. So in this figure, we're trying to show the timing for the situation with and without the use of interrupts. You may see that there is still a gain in efficiency because part of the time during which the IO operation is underway overlaps with the execution of the user instruction. So now we have this same figure we saw before, but now we include the interrupts. So just maybe thinking about this again. So we have the fetch, the instruction fetch, the operand fetch, the operand store. We have all this up here. And so this is where we now can have this interrupt that we can service. And when we're done, we go back to continuing in this process. And so this is a slight update to the one that we saw previously. Just going back, maybe I can try and cycle back. So we had this one back in figure 3.6. Now we're going to this figure. We can see the changes by adding the interrupt. So two approaches can be taken to dealing with multiple interrupts. The first is to disable interrupts while the interrupt is being processed. So you can't interrupt an interrupt. A disabled interrupt simply means that the processor can and will ignore that interrupt request signal. If the interrupt occurs during this time, it generally remains pending and will be checked by the processor after the processor has enabled interrupts. So here we see sequential interruption, and then we see nested interruption. So maybe we have a higher interrupt that takes place. So those are the possibilities that we can be thinking about here. And we're trying to illustrate both of those in this figure. So let's think about this in more detail. Here we have an example, the time sequence of multiple interrupts. So there can be a whole bunch of things that are constantly tapping on the shoulder of the computing environment to be helping it think about what it should do. So this is a second approach. So consider a system with 3 IO devices, a printer, a disk, and a communication line, with increasing priority. So how are we going to handle each one of those? And so there's an interrupt service routine. While the routine is executing, we can be seeing how that could be working. And so here we can be thinking about the times that it's going to be taking to do each one of those interrupts. So that's just a quick little summary there for what we're trying to accomplish. So we see the printer doesn't interrupt, and during the printing cycle, we get an interrupt. And so you can be pausing the printer to handle a communication interrupt. And right after that, we get another interrupt for a disk service routine, and then go back and finishing the printer. So thus we can be seeing that we end up having a little bit of a delay, say 10 seconds or so for the communication, and another 10 seconds for the disk operation, and then we can return back for this completion at the end. Okay, well, let's continue on now. So let's now think in terms of the I/O functions. So an I/O module, for example, a disk controller can exchange data directly from the processor, just as a processor can initiate a read or write with memory designated the address of a specific location. The processor can also read data from or write data to an I/O module. In this latter case, the processor identifies a specific device that is controlled by a particular I/O module. Thus, an instruction sequence similar in form to that of figure 3.5 could occur. The I/O instructions rather than memory reference instructions. In some cases, it is desirable to allow I/O exchanges to occur directly with the memory. In such a case, a processor grants to an I/O module the authority to read from a write to memory so that the I/O memory transfer can occur without trying to tie up the processor. During such a transfer, the I/O module issues read or write commands to memory, relieving the processor responsibility for the exchange. Thus, this operation is known as direct memory access, and so we'll be coming back to that in chapter 7. So we're getting a little bit more details of how we think about doing the I/O functions. And here we have a figure. A computer consists of sets of components or modules of three basic types: the processor, memory, and I/O. And so these are the three main elements. These are the three elements in a von Neumann architecture, the three main elements in a computing environment. So they all communicate with each other. And in effect, a computer is a network of basic modules. Thus, there must be paths for connecting the modules. And so this is what we're starting to be thinking about, the inputs and outputs for each. The collection of paths connecting the various modules is called the interconnection structure. The design of the structure will depend on the exchanges that must be made among modules. So in this figure, it suggests that the types of exchanges that are needed by indicating the major forms of input and output for each module. For the memory, we have typically a memory module consists of n words of equal length. Each word is assigned a unique numerical address. A word of data can be read from or written into the memory. The nature of the operation is indicated by read and write control signals. The location for the operation is specified by an address. So that's the first thing for memory. For I/O, from an internal point of view, I/O is functionally similar to memory. There are two operations, read and write. Further, an I/O module may control more than one external devices. We can refer to each of the interfaces to an external device as a port and give each a unique address. In addition, there are external data paths for the input and output of the data with the external device. Finally, an I/O module may be able to send interrupt signals to the processor. And finally, the third part, for a processor, the processor reads in the instructions and data, writes out data after processing, and uses control signals to control the overall operation of the system. It also receives interrupt signals. Okay, continuing on. So, sorry. So the interconnection structure must support the following types of transfers. So we have the memory to processor. The processor reads an instruction or unit of data from memory. We have the processor to memory. The processor writes or a unit of data to the memory. We have the I/O to processor. The processor reads data from an I/O device via an I/O module. We have the processor to I/O. The processor sends data to the I/O, and the I/O to or from memory. For these two cases, an I/O module is allowed to exchange data directly from memory without going through the processor using direct memory access, DMA. So those are the things that we have here in this, that we're getting some more insight into how we can be doing the various types of transfers. Okay, now in terms of the bus interconnects, the bus was the dominant means of computer system component interconnects for decades. For general purpose computers, it was gradually given way to point-to-point interconnect structures, which now dominate computer system design. However, bus structures are still commonly used for embedded systems, particularly microcontrollers. So microcontrollers are scaled down processors that are used for things like Internet of Things, IoT, which we'll be talking about later. So that's something that we want to be keeping in mind. In this section, we will give a brief overview of the bus structure, and Appendix A in the textbook has more details if you're interested and you wanted to look that up. So bus is a communication pathway connecting two or more devices. A key characteristic of a bus is that it is a shared transmission medium. Multiple devices connect to the bus, and a signal transmitted by any one device is available for reception by all other devices attached to the bus. If two devices transmit during the same time period, the signals will overlap and become garbled. Thus, only one device at a time can successfully transmit. Typically, a bus consists of multiple communication paths or lines. Each line is capable of transmitting signals representing binary 1 and binary 0. Over time, a sequence of binary digits can be transmitted across a single line. Taken together, several lines of a bus can be used to transmit binary signals simultaneously, that is, in parallel. For example, an 8-bit unit of data can be transmitted over 8 bus lines. So computer systems contain a number of different buses that provide pathways between components of various levels of the computer system hierarchy. A bus that connects major computer components, processor, memory, and I/O, is called a system bus. The most common computer interconnection structures are based on the use of one or more system buses. So that's that gives a good overview of that. So let's now get into data buses. A system data bus typically is about 50 to 100 separate lines. The data lines provide a path for moving data among system modules. These lines collectively are called the data bus. The data bus may consist of 32, 64, 128, or even more separate lines. And so those are all possible. The number of lines being referred to as the width of the data bus, because each line can carry only one bit at a time, the number of lines determines how many bits can be transferred at a time. The width of the data bus is a key factor in determining the overall system performance. For example, if the data bus is 32 bits wide and each instruction is 64 bits long, then the processor must access the memory modules twice during each instruction cycle. Okay, let's think about the address bus and the control bus. So let's go ahead and think about these one at a time here. So first of all, the address bus is used to address the source or destination of the data on the data bus. The width determines the maximum possible memory capable of the system. The control bus is used to control the access and the use of the data and the address lines. Because the data and the address lines are shared by all components, there must be a means of controlling their use. Control signals transmit both commands and timing information among system modules. Timing signals indicates the validity of data and access information. Commands signals specify operations to be performed. So thus we see a couple other types of buses here that are part of the computing architecture. Here we're seeing another illustration of the bus interconnection scheme. So the memory, the CPU and the IO all are connected. So we're seeing the control lines, the address lines, and the data lines. All of these need to be connected to each one of these three major modules, the CPU, the memory, and the IO. You can have multiple memory modules, you can have multiple input and output devices, and we're trying to give an illustration of what that would look like by that figure. Well, we mentioned this, but now let's talk about point-to-point interconnections. And so the shared bus architecture was a standard approach to connecting interconnections between the processors and the other elements for decades, but contemporary systems are moving more to this direction of point-to-point interconnects. The principal reason driving this change from bus to point-to-point interconnects was the electrical constraints encountered with increasing the frequency of synchronous buses. At higher and higher data rates, it becomes increasingly difficult to perform the synchronization and arbitration function in timely fashions. So thus we see that this movement is important. So if we just walk through this chart, it gives us an idea of how we would go through this. So trying to do the synchronization is hard. At higher data rates, it becomes difficult. A conventional shared bus on the same chip magnified the difficulties. And finally, it has lower latency, higher data rates, and better scalability. So that's the reason why we're going to point-to-point interconnects. What about quick path interconnections? This is something that was introduced in 2008. And so here are a couple of key points for them. First of all, the multiple direct interconnects, multiple components within the system enjoy direct pairwise connections to other components. This eliminates the need for arbitration found in shared transmission systems. For the layered protocol architectures, as found in network environments such as TCP/IP-based data networks, these protocol level interconnects use a layered protocol architecture rather than the simple use of control signals found in shared bus arrangements. Finally, packetized data transfers. Data are not sent as a raw bit stream. Rather, data are sent in a sequence of packets, each of which includes control headers and error control codes. So in this figure, we're illustrating a typical use of QPI as a multi-core computer. The QPI links indicated by the green arrows pairing in the pairs in the figure form a switch fabric that enables data to move throughout the network. And so we can be seeing this movement with the QPI between modules. So I'm just going to go ahead and move on. So here we can be thinking of the layers of the QPI. First of all, we have the physical layer. It consists of the actual wires carrying the signals, as well as the circuitry and logic to support ancillary features required in the transmission and receipt of the ones and zeros. The unit of transfer of the physical layer is 20 bits, which is called a PHIT, P-H-I-T, a physical unit. The link is responsible for reliable transmission and flow control. The link layer unit of transfer is an 80-bit FLIT. And so that's the next level. We have the routing. This provides a framework for directing packets through the fabric. And finally, protocol. the high-level set of rules for exchanging packets of data between devices. A packet is comprised of an integral number of flits. So that's a couple of things to be thinking about in terms of definition. Here we can see the physical interface of the Intel QPI interconnect. And so we have transmission lines going between components, transmission and reception, transmission lanes and reception lanes as indicated in this figure. Here we have an illustration of a QPI multi-lane distribution. And so another function performed by the physical layer is it manages the transmission between 80-bit flits and 20-bit fits using a technique known as multi-lane distribution. So you cycle between one at a time, and then you go one to another in each one of these lanes. That's what we're trying to show in that figure. For the QPI link layer, it performs two key functions, the flow control and error control. These functions are performed as part of the QPI layer, link layer protocol and operate on the level of the flit flow control unit. Each flit consists of 72-bit message payload and a 8-bit error control code called a cycle redundancy check, CRC. This is something that we'll talk more about in chapter 5. A flit payload may consist of data or message information. The data flits transfer the actual bits of data between cores or between a core and a IOH. The message flits are used for such function as flow control, error control, and cache coherence. This is something that will be discussed further in chapter 5 and chapter 17. The flow control function is needed to ensure that a sending QPI entry does not overwhelm a receiving QPI entry by sending data faster than the receiver can process the data and clear buffers for more incoming data. To control the flow of data, QPI makes use of a credit scheme. During initialization, the sender is given a set of numbers of credits to send flits to a receiver. Whenever a flit is sent to the receiver, the sender decrements its credit count by 1 credit. Whenever a buffer is freed, at the buffer, a credit is returned to the sender for that buffer. Thus, the receiver controls that pace at which the data is transmitted over a QPI link. Occasionally, a bit transmitted at a physical layer is changed during the transmission due to noise or some other effect. The error control function at the link layer detects and recovers from such bit errors and so isolates higher layers from experiencing bit errors. The procedure works in a cool way, so I'm not going to get into the details for at the moment here. Okay, here is the final chart on QPI. I'll quickly go over this and then just review simply because this is probably complicated and maybe hard to follow. So we have two other protocol layers that we want to be thinking about, the routing layer and the protocol layer. The routing layer is used to determine the course that a packet will travel across the available system interconnects. And it's defined by firmware and describe the possible paths that a packet can follow. The protocol layer is a packet is defined as the unit of transfer. One key function performed at this level is a cache coherency protocol, which deals with making sure that main memory values held in multiple caches are consistent. Typical data packet is a block of data being sent to or from a cache. So let's just quickly review here. So the QPI is something that was introduced in 2008. It has multiple direct connections, layered protocol architecture, and it has a packetization of data. So it's leveraging things that have been used in other areas and then applying it towards input and output. A packetized like a TCP/IP, layered protocols for doing correction, and having multiple direct interconnects. Here's an example of those multiple direct interconnects in terms of a multi-core configuration, an illustration of the layers that make part up the ways that it is done, the physical link, routing, and protocol, the way that you can be connecting between components. And so this would be specifically between two components, like what we're showing here, but now we're just focusing on two individual components to get some perspective on that. So we then saw that you can have those lines that are connected to be shared, and then you can route one to another and make some uses of that. Then we went into some more details of each one of those protocols. Okay, next we'll talk about something that may be a little bit more familiar to you, and that's the PCI peripheral component interconnects. It's a popular high bandwidth processor independent bus that can function as a mezzanine or peripheral bus. Delivers better system performance for high-speed I/O systems. PCI special interest group was created to develop further and maintain the compatibility of PCI specification. And then there's also something called the PCI Express. It's a point-to-point interconnect scheme intended to replace bus-based schemes such as PCI. So the key requirement is high capacity support the needs of high data rate I/O devices such as gigabit Ethernet. Another requirement deals with the needs to support time-dependent data streams. So thus we get a chance to be thinking about PCI, and then PCI Express is what we're talking about here as we go through this information. So PCI, Intel began to work on PCI in the 1990s, so that's been around for quite a while. And now with this new version, the PCIe has been developed as with QPI, and you can see some of the characteristics of QPI showing up. It's a point-to-point interconnect scheme. And so that is a slight difference from what we're talking about between just a general PCI bus. This PCI is more like a general bus. PCI Express is trying to be getting the advantages of a point-to-point architecture. So here are some typical configurations using PCIe. And so a root complex device, also referred to as a chipset or a host bridge, connects the processor and memory subsystem to the PCI Express switch fabric, comprising of one or more PCI or PCI switch devices. And so you can think of the chipsets as a lot of times what's on the motherboard or the system board associated with a processor. And so that's what we're talking about here. The root complex acts as a buffering device to deal with differences in data rates between I/O controllers and memory and processor components. The root complex also translates between PCI transaction formats and the processor and memory signals and control requirements. The chipsets are typically support multiple PCIe ports, some of which attach directly to PCIe devices, and one or more that attach to a switch that manages multiple PCIe streams. PCIe links from the chipsets may attach to the following kinds of devices: switches, PCIe endpoints. They can switch to legacy endpoints, and PCIe/PCI bridges. All of these are the kind of things. And so this is like a Swiss Army knife for connections, and there's a lot of different things that are available within its wheelhouse of capability. So similar to the QPI, we had this same kind of layers here, but there's only three. We have the physical, the data link, and the transaction. This is what we see for the PCIe point-to-point interconnection. The physical consists of the actual wires carrying the signals, as well as the circuitry and logic to support ancillary features required in the transmission and receipt of the ones and zeros. The data link is responsible for the reliable transmission and flow control. Data packets generated and consumed by the DLL are called data link layer packets. So that's what DLLP is, an acronym that tries to capture that, seeing that there. And finally, the transactions, this generates and consumes data packets used to implement load/store data transfer mechanisms that also manages the flow control of those packets between the two components on a link. Data packets generated and consumed by the TL are called transaction layer packets. Above the TL, the transaction layer are software layers that generate read and write requests that are transported by the transaction layer to the IO devices using a packet-based transmission protocol. So that gives you a little bit more insight into how the PCIe works. And similar to the QPI, the PCIe is an end-to-end point architecture. Each PCIe port consists of a number of bidirectional layers. Note that a QPI, the lanes refer to transfers in one direction only. And you might remember we saw that with this connection diagram, that you're either going in one direction or the other. That's not true for what we're trying to show for this. Each PCIe port consists of a number of bidirectional lanes. Transfer in each direction in a lane is by means of a differential signaling over a pair of wires. The PCIe port can provide 1, 4, 6, 16, or 32 lanes. So there's information in the text for the PCIe 3.0 specification that was introduced in 2010. And so we can be thinking about some of the details there. And in this figure, it shows an example for a PCIe port consisting of 4 lanes. Data are distributed by the 4 lanes, 1 byte at a time, using a simple round-robin scheme. And each physical layer, data are buffered and processed 16 bytes at a time. Each block of 128 bits is encoded into a unique 130-bit code word for transmission. This is a reference to 128-bit / 130-bit encoding. Thus, the effective data rate of the individual lane is reduced by a factor of 128 over 130. So there's a little bit of other factors that are going on here to allow for control of what we're trying to accomplish and make sure that things work properly. So there's more information in the textbook that you can refer to, but I'm just going to leave it there for that type of a discussion. Here we see a PCIe transmit and receive block diagram. So a common approach, and the one used in PCIe 3.0, is overcoming the problem of a long string of bits, or one value is scrambling. Scrambling, which does not increase the number of bits by transmitting, is mapping technique that tends to make the data appear more random. The scrambling tends to spread out the number of transmissions so that they appear at the receiver more uniformly spaced, which is good for synchronization. So we're getting some interesting, more complex way of doing our architecture that is trying to spread things out and use all resources in a more constant fashion. Also, another transmission other transmission properties, such as special properties, are enhanced if the data are more nearly of a random nature rather than constant or repetitive. Another technique that can aid in synchronization is encoding, which additional bits are inserted into the bit stream to force transitions. So you can see that there's a fair amount of complexity that we have in this type of device. And probably this is getting into more details than most of you will have to deal with as you go forward after this class. For PCIe transaction layer, it receives read and write requests from the software above the TL level and creates request packets for transmission to a destination via the link layer. Most transactions use a split transaction technique. A request packet is sent out by a source PCIe device, which then waits for a response called a completion packet. TL messages and some write transactions are posted transaction, meaning that no response is expected. TL packets format supports 32-bit memory addressing and extends 64-bit memory addressing. Okay, so the TL supports 4 addressing spaces: memory, configuration, IO, and messaging. The memory space includes system main memory. It also includes PCIe IO devices. Certain ranges of memory devices map into IO devices. IO, the address space, is used for legacy PCIe devices with reserved memory address ranges used to address legacy IO devices. Configuration, this address space enables the TL to read, write configuration registers according associated with IO devices and messages. The address space is for control signals related to interrupts, error handling, and power management. So here is a table of PCIe TLP transaction type. And so we're showing some of the summary details that may be helpful for you to get a better sense of how all of this is used. So we see a couple of things here. The different type of transaction types for memory. I'll just focus on the purposes in this table. So the memory, the transfer data to or from a location in the system memory map. For the IO, this deals with the transfer data to or from a location in the system IO write request memory map for legacy devices. For the configuration, this is for transfer data to or from a location in the configuration space of a PCI device. The message, this provides in-band messaging and event reports. And finally, memory and IO configuration, this provides return for certain requests. And so there's a fair amount of things that are done with the PCIe, and we can see some next level type of performance that's included with this. Here we see the PCIe protocol data unit format. So we can have an overall the things that are captured with a physical layer. So the largest amount of information, the data layer, and then the transaction layer here. So we see that there's a total number of things that increases as we put this all together for this complete thing here that we're showing in this table. So a TLP originates in the transaction layer of the sending device and terminates at the transaction layer of the receiving device. Upper layer software sends to the TL the information needed for the TL to create the core of the TLP, which consists of the following fields. So we have headers. The header describes the type of packet and includes information needed by the receiver to process a packet, included any needed routed information. The internal header format is discussed subsequently later in the text. So for data, a data field of up to 4,096 bytes may be included in the TLP. Some TLPs do not contain a data field. We have the ECRC. It's an optional end-to-end CRC field. Enables the destination TL layer to check for errors in the header and data protocols of the TLP. And so that's the purpose of the PCLE data link layer, is to assure reliable delivery of the packets across a PCLE link. The DLL participates in the formation of the TLPs and also transmit DLLPs. Data link layer packets originate at the data link layer of a transmitting device and terminates at the DLL of the device on the other end of the link. So in figure 325B over here shows a format of the DLLP. There are three important groups of the DLLP used in the managing a link flow control packets, power management packets, and TLP acknowledge and NAC packets. Power management packets are used in managing power platform budgeting. Flow control packets regulate the rate at which TLPs and DLLPs can be transmitted across a link. The ACK and NAC packets are used in TLP processing, discussed in later in the textbook. I think I'm not going to get into those details. You can feel free to read more about this in the textbook, but that's a quick synopsis for the last part of this, the PCI protocol and how it works. Okay, so we have covered a lot of information in this chapter. Hopefully this will be a chapter that will help clarify things, maybe give you some context as we start to first build upon the introductory material that we've talked about in the first two chapters, and now get into more details about thinking in terms of a top-level computing function and the various interconnects. We got a chance to talk about computer components, talked a little bit more about the von Neumann architecture. We talked about in functions, we talked about the fetch execute cycle. We talked about how the interrupts start to impact that. And then we started to talk about input and output functions. We talked about historically that there was the bus interconnects and various types of interconnection structures. And since then, there has been more complicated ways of doing interconnects. The first one being the point-to-point interconnect. And so we went through the various layers of the QPI interconnect method. And then we talked about the PCI as well as the PCIe way of doing interconnects. And we can see how the PCIe has similar features to what we find in the QPI, and how we can create a fairly flexible interconnect construct where that the wiring itself can manage dealing with the protocols of different types, legacy and state-of-the-art components, all in the same infrastructure. Okay, that's it for this chapter. So we've gone through the introduction, the basic concepts, and performance, ways of having performance metrics for computing systems. And now we just talked about this top-level view of computing. And so we'll go ahead and call it a day for chapter 3. Thank you.